Hi, this is Elliot from EO Nutrition. Today's setup is slightly different. I'm actually using my laptop because I've put together some presentation slides on PowerPoint, which I'm going to be sharing. The reason I'm doing this is because the topic at hand today is a little bit more dense, and I think that you as the audience would probably benefit from being able to see the slides and the PowerPoint diagrams while I'm speaking today. So to introduce the topic, what I'm actually going to be talking about is how sulfate, which is a form of sulfur which you get from the diet and various other places, how sulfate is absolutely critical for blood flow. Okay, we're going to be looking at not just biochemistry, but I guess what you would call biophysics, how sulfate has an effect on water, which actually causes it to structure or form an exclusion zone, and how this exclusion zone in water is likely involved in maintaining healthy blood flow and healthy vascular health. All right, good vascular health. We're also going to be looking at how this exclusion zone might play a role in cellular physiology, and then we're going to be looking at how if things go wrong, how this might affect the human body. So if I change the screen to the PowerPoint and we start from there. So yeah, so it's called sulfate. Oh, sorry. I'll go back. So the topic of today's talk is called sulfate, exclusion zone water, and blood flow. So first of all, before we go into the details, for the audience members who who are not familiar with sulfur, we are going to cover the basics. As I said, it's not going to feature much biochemistry today, but we are going to have to just briefly go into how the body derives sulfate from the diet, and really how that kind of works to give you a good introduction. So to start off with, sulfur, as I said, it's an essential element found in the Earth's crust. When I say essential, it means that your body needs it because it can't produce it itself. So it needs to get it in from the diet or via the water. It's the 8th most abundant mineral in the human body. And sulfur exists in many different forms. These are technically referred to as the oxidation states. This is basically referring to their chemical state. And so as multiple different forms being sulfate, sulfite, sulfane, and sulfide. So you may have heard of sulfite before because that's what they use as a preservative for things like wines and dried fruits. Whereas what we're going to be concerning ourselves with today is the first form, and this is sulfate. Okay. Now, this is the most highly oxidized form of sulfur, and sulfate is really what we need to do the things that we need to do. So we can take many other forms of sulfur or types of sulfur or sulfur from different foods, and we really need to convert them into this usable active form called sulfate. Okay. Now, when we look at sulfate as an ion, essentially sulfate is classified according to something called the Hofmeister series as a cosmotrope. So just to give the reader or the listener some background, the Hofmeister series is essentially a classification system, and it's used to classify various ions based on their ability to interact with and organize proteins in the solution. But this also applies to their interactions with water. So I'll give you an example. A chaotrope. A chaotrope is essentially something which is able, or a type of ion, which is able to induce disorder in neighboring water molecules. Okay, so it promotes what we call bulk water. Bulk water is basically the kind of water that you find coming out of your tap. If you were to pour water into a glass, that would be bulk water. Whereas on the other hand, you have cosmotropes. And cosmotropes actually have the opposite effect on surrounding water molecules. They can actually, rather than inducing disorder, they actually organize water. They can organize the water which is surrounding the ion into something which resembles a gel. So sulfate, as I said, it's a strong cosmotrope. And this means it has a very strong gelling effect on water. Now, you might be wondering why I'm talking about this, but later on you will appreciate it, because you need to know this to understand how sulfate might actually be important for blood flow later on. Okay. So just to cover the basics again, the main sources of sulfur, we get some inorganic sulfate in the water that we drink. And this varies from area to area, depending on the sulfate of the local water supply. The main source of sulfur is actually going to come from amino acids. So these are methionine, cysteine, and taurine. These are found very, very heavily in animal foods, not much in plant foods. You also have dietary glutathione, okay? And this is because cysteine is, to make glutathione, you need 3 amino acids. You need glycine, you need cysteine, and you need glutamate. So to make glutathione, you need those 3, and that's why glutathione is called a tripeptide. Tri meaning 3 different amino acids needed to make it. So when you eat meat, meat contains a small amount of glutathione. When you eat certain fruits and vegetables, they contain small amounts of glutathione as well. There is also the sulfated glycosaminoglycans, such as those found in the connective tissue. You would get these from your bone broths and your fatty cuts of meat, which contains lots of connective tissue, collagen, skin, that kind of stuff. To add to that, you also have certain volatile organosulfur compounds, and these are the things which you find in cabbages, in broccoli, the allium family, the brassica and cruciferous vegetables, the kale, cauliflower, onion, garlic, that kind of thing. And the exact chemicals, well, these include isothiocyanates, glucosinolates, and sulforaphane, which you may have heard of. Sulfur is also contained small amounts in some of the B vitamins. So you have biotin and you have thiamine. So, as I said before, we're not going to go into too much of the biochemistry today. However, just to give you a very brief overview, and I don't want to go into too much detail here, but as a brief overview, when you're taking various forms of sulfur from the diet, most of it is going to come from the amino acids, and that is probably going to be methionine and cysteine. However, if you recall that I said to be able to use sulfur, most of the uses actually require you to make inorganic sulfate. This is the most oxidized form of sulfur. And you can make this from these amino acids. So I'll give you an example. You take methionine, you get high levels of methionine, you eat a steak. You need to convert the methionine into sulfate. And the way that you do that is via something called the methylation cycle. So we derive methyl groups from methionine, and it goes through all of these steps to get to homocysteine. Homocysteine alternatively can go back up towards methionine, or it can go down towards cysteine. Now, homocysteine can be converted into cysteine via the use of B6 and then another enzyme, cystathionine gamma lyase. But essentially, you can make cysteine from methionine. You also get cysteine usually in the same foods that you get methionine. So cysteine is very high in eggs, dairy products, all forms of animal products. And so you can essentially take cysteine straight away and you convert that into taurine or sulfate. Okay. So just to recap, you need to make sulfate. You can do this via taking dietary amino acids, passing them through loads of chemical reactions, the methylation cycle and the transsulfuration cycle, to get to this step where you get sulfate. But it's not quite that easy. Once you've got cysteine, cysteine also has to go through several different steps to be able to make sulfate. Cysteine has to first go through 2 chemical reactions, and then you may produce taurine or you may produce sulfate. But to get to sulfate, you need to produce sulfite. Okay, so you take sulfite and you pass it through an enzyme there called sulfite oxidase, and this uses molybdenum as a cofactor. Now, when you pass sulfite through that enzyme, that's when you get the inorganic sulfate, and that's exactly what you need. Okay, now unfortunately, if someone has some kind of molybdenum deficiency, then this is theoretically going to cause a buildup of sulfite, which is toxic, by the way, and less sulfate. So this is theoretically going to reduce our capacity to take sulfate from the amino acids methionine and cysteine. Okay. Now, I've titled this Many Roads Lead to Sulfate, and this is because all of those dietary forms of sulfur that we saw before, coming from the vegetables, from the meat, whatnot, these need to be converted into inorganic sulfate. I cannot emphasize that point enough, okay? Now, inorganic sulfate is then activated with the use of ATP, and the active form of sulfate is actually critical for a set of reactions which are called sulfation reactions. Okay, you may have heard of sulfation in the context of detoxification, and I believe this is usually referring to sulfate conjugation. Okay, so this is where what we do is we take sulfate and we conjugate it with some kind of toxin or some hormone or a neurotransmitter or a drug, something that we need to get rid of, and that's one of the ways in which we detoxify it. Okay. At the same time, sulfation is not only important for detoxification, but sulfation is also extremely important for the synthesis of various things in the body. So it's needed for the production of these structural elements called mucins. It's needed for gastrointestinal hormones such as cholecystokinin and gastrin. It's needed for digestive enzyme synthesis. Okay. It's also needed for the production of what we call sulfated glycosaminoglycans. Okay, so this is where you really need to pay attention, because this is quite important. The sulfated glycosaminoglycans are essentially, there's many different types. So as you can see, I've listed them here. You have chondroitin sulfate, heparan sulfate, dermatan sulfate, all of these different things, and you generally find them. They decorate the exterior of every single cell. They make up a large portion of what is called the extracellular matrix, which is basically the space in between the cells. And there's quite a lot of space in between the cells. And so when you look at what a sulfated glycosaminoglycan actually is, it's a hydrophilic carbohydrate chain, or let's say many different chains. Okay, so there's a diagram here, many different chains coming from a protein from such as collagen, or such as the cell membrane. And essentially what we see is sulfate is essentially dotted all along the surface of the chain. Okay, and this essentially provides the glycosaminoglycan with a very dense negative charge. All right, so you can see what these lines represent is essentially negative charge. So glycosaminoglycans are they essentially envelope the cell, or they decorate the cell, and they provide the exterior or the surface of the cell with an extremely dense negative charge. And so to transport sulfate, this requires something else, actually, because if you remember me saying, sulfate is a cosmotrope, meaning that it gels water, and the blood is made of a large portion of water. So too much sulfate traveling in the blood at any one time could potentially thicken it, cause it to become so thick that it didn't flow, and that would be potentially fatal. So that's not what the body wants to do. So we have to keep fairly tight limits on the amount of free sulfate that travels through the blood. And therefore, we manage to transport sulfate in various other ways. Now, the list here, there have been various functions attributed to these things. But one of the researchers who actually specializes in sulfate, or probably the most well-known researcher in the field of sulfate at the moment, she hypothesizes that all of these molecules are actually novel ways to transport sulfate around the body without having to thicken up the blood excessively. Okay, so as you can see, the body really likes to attach a sulfate to various different molecules, hormones, neurotransmitters, etc., etc. Okay, now one of the sulfated steroids is actually cholesterol. And as you can see, what you can do is you can take cholesterol and bind it with sulfate to produce cholesterol sulfate. And this is a particularly intriguing way to transport sulfate around the body, because as you see, cholesterol is not usually soluble in the blood. And this is why you have HDL or LDL transporters. And these are essentially, they're there to transport cholesterol, okay? So when you go to your doctor and you look at the blood sample, you might have HDL, LDL. It's not referring to cholesterol, it's referring to lipoproteins which transport the cholesterol. Interestingly enough, when you sulfate cholesterol, what happens is you actually turn it into something called amphiphilic, okay? And this means that it's soluble both in fat and in water. So it means that it can start traveling through the blood. And this is potentially a unique way to transport both cholesterol and sulfate throughout the body to get to where it needs to go. Now, I just want to take the time here to say that really much of the credit for this whole presentation has got to go to Dr. Stephanie Seneff, because quite frankly, I think she's a genius. All of this information has been derived from her papers and the research that she's done. And so I really would highly recommend any of the listeners who are interested in learning the details about this topic, I would really recommend that they go to Dr. Stephanie Seneff's website and they read some of her papers. I'll make sure to link some below this video, okay? Now, just one more thing to add. When you have cholesterol sulfate, one of the main ways that it travels is actually it dots onto the membrane of the red blood cell, okay? And this provides the red blood cell with a very dense negative charge. Now, the way that your body produces cholesterol sulfate, I guess this is up for debate. I'm not sure if anyone knows, but there is one hypothesis by Dr. Stephanie Seneff, who essentially posits that one of the enzymes in the skin called endothelial, or well, actually in the blood vessels called endothelial nitric oxide synthase, is proposed to have a dual role. One of the roles is to produce endothelial nitric oxide, but another role is actually to produce cholesterol sulfate. Okay, and so the role of sunlight, or there is a proposed role of sunlight, in that sunlight touching the skin not only synthesizes vitamin D, but actually it's one of the main ways that the body sulfates cholesterol. Okay. Now, you're probably wondering at this point, what am I talking about? What does sulfate have anything to do with blood flow and with water? And how is any of this going to make sense? Well, essentially, I've covered the basics so that the listeners can get a brief understanding of the kind of terms that we're referring to. We're talking about cholesterol sulfate when we're talking about sulfation. And when we're looking at blood flow. Okay, so from this point onwards, I hope that the listener can hopefully have like a basic understanding of what I'm talking about, because here's where we're going to go into some of the details of how sulfur is actually so essential for the blood to flow. Okay, so essentially, as I said, you have cholesterol sulfate dotted on the exterior of the red blood cell. Okay, and red blood cells, when they are flowing through the blood, you don't want it to be too thick. You don't want the blood to be too thin, and you don't want the blood to clot together. You don't want red blood cells to aggregate, because that is essentially how you get a blood clot, and that is potentially fatal. So that's something that you really don't want. So a healthy blood actually has something called a high zeta potential. When I say zeta potential, this is the term referring to the measurement of the repulsion between similarly charged particles in suspension. Okay, in the context of the blood, what this basically means is the degree of repulsion or between the red blood cells. So if you've got red blood cells flowing through the blood, it's how much those red blood cells are repelled from one another. Okay, if there's a good degree of repulsion, then that essentially means that they're not likely to stick together and clot and aggregate. Okay, if there's not much repulsion, then they do start to aggregate. Okay, now to be able to maintain the high zeta potential, you use something called sialic acid, but you also need cholesterol sulfate. Okay, as you can see on this diagram, the exterior of the red blood cell membrane is actually there's a net negative charge, and that negative charge, what contributes to the negative charge, is the cholesterol sulfate and the sialic acid. Okay, now if there is enough cholesterol sulfate on the red blood cells, you maintain a high zeta potential, which means there's a highly repulsive force from one another, and this means that the blood is not likely to clot. Now, the way to think about this, the way that I like to think about this, okay, imagine if you had two magnets, and imagine if you had the negative side of one magnet and the negative side of another magnet, and you tried to pull them together. What would happen? Well, they would be repelled from one another. You wouldn't be able to put them close together. Likewise, if you turned it around and you got the positive side and then the positive side, and you tried to put them together, there is a repulsive force. Opposites attract, okay? Likes repel from one another, and that's essentially, if you can imagine this is a red blood cell and this is a red blood cell, then by maintaining that negative charge is so important. By maintaining the negative charge, what you're doing is you're stopping them from clumping together. And the point that I'm trying to make is that the negative charge is provided by adequate levels of cholesterol sulfate. Okay? Now, let's start to look at the blood vessels. We've just looked at how the blood likely stops, or what likely stops the blood from aggregating, the blood cells from clotting. But now we're going to have to look a little bit more closely at the blood vessels. So inside the blood vessels, the vascular epithelial inner lining is actually called the endothelial glycocalyx. Okay, so the glycocalyx is basically thick, fuzzy coating, as you can see here, lots of hair-like projections. And if you look really closely, the hair-like projections are actually rich in sulfated glycosaminoglycans. These are the things that we were looking at before. If I go back, sulfated glycosaminoglycans. These are extremely dense with negative charge. Remember, you need sulfate in its active form to be able to synthesize sulfated glycosaminoglycans. And so the endothelial glycocalyx is rich in negative charge. So here's another diagram where you can see this is meant to be the inside of the blood vessel. These projections coming out with the sulfate attached. A likely candidate for building structured, easy water. Okay. Now, what do we mean when we're talking about exclusion zone water? So essentially, exclusion zone is another word for structured water. And if I'm sure many of the audience are familiar with the work of Dr. Gerald Pollack. If you're not, then I would highly recommend that you go and you read some of his books, you read some of his papers, and listen to his interviews, and watch some of his videos on YouTube, because his work is absolutely fascinating. In short, what they found is that water within living systems, such as in the human body, actually contributes toward biological functions in very specific ways. In that, water inside the body is not the same as liquid bulk water. In other words, it's not the same as the water coming out of your tap. Okay, there are significant differences between bulk water and the water that is inside your cells and bathing your cells. In fact, much of the water inside the body is most likely gel. Okay, and what do I mean by that? Well, essentially, when water comes into contact with a hydrophilic surface, such as a protein, which is the case inside the human body, when it comes into contact with a hydrophilic surface, it essentially you get charge separation. Okay, so what this means is that you have the positively charged protons of water actually being pushed away from the surface, whereas you have this very dense domain, this dense layer of what is called an exclusion zone of negative, of electrons, essentially, of negative charge. The reason it's called exclusion zone is because aside from excluding protons, it also excludes many other solutes. It excludes everything. Okay, so what it essentially does, it acts a bit like a motor. Okay, this phase, it's also referred to as the fourth phase of water, because it's not quite solid and it's not quite liquid, but it's somewhere in between. Okay, its structure resembles that of a liquid crystal, and there have been various other people who have proposed in the past that water exists in similar states. Okay, and so when you get this charge separation, as I said before, immediately on the hydrophilic surface, you have this domain dense with electrons, but what it's doing is it's pushing protons away. And so you have the distribution of positive and negative charge on either side actually is theorized to create something a bit like a battery or a motor. As I said, it excludes solutes. It moves things. And it does this without the use of ATP, without the use of biochemical energy. And funnily enough, you can build the exclusion zone. So you can charge up the battery. You can charge up the battery inside the water by sunlight. So various types of incident energy, various types of light have actually been shown to greatly, almost essentially inject energy into the battery in the form of incident energy, and that actually increases the size of the exclusion zone. So you have UV light, you have visible light, but most of all, really, you have infrared light. Okay, and these are all found in sunlight. So this again is pointing to sunlight as potentially very important in this whole process. Now, for the listeners who aren't familiar, I would highly recommend reading the following book. So you have The Fourth Phase of Water by Gerald Pollack. He also wrote a very good book called Cells, Gels, and the Engines of Life. And then there is also the work, some of the books from the late Mae Won Ho. She was also a very talented researcher in the field of water, and she wrote a book called Living Rainbow H2O, and I would highly recommend reading that. Furthermore, to get just a brief introduction of how structured water may actually be involved in how the cells work, in how information is conveyed throughout the body, I have written in a little bit more detail on one of the articles on my website, and that's called The Living Matrix and Structured Water. But now, so to get back to the glycocalyx and sulfate. Okay, back to what we were talking about. Just to recap, we spoke about how the red blood cells have cholesterol sulfate dotted on the cell membrane, and this provides them with negative charge. They have a very dense negative charge. This stops the cells from clumping together. Now we're going to be talking about the inner lining of the blood vessel. When we look at the inner lining of the blood vessels, we see that the sulfated glycosaminoglycans are very good candidates for building structured water. They are hydrophilic. They have dense negative charge, and the sulfate is a cosmotrope, which means it naturally has a structuring effect on water. So here is a diagram from one of Stephanie Seneff's papers, which essentially gives you some imagery of how this might look. So here is the endothelial cells lining the blood vessel. Here you have the sulfated glycosaminoglycans, and here is a negatively charged exclusion zone of water. Okay, so it's very likely that lining the inner blood vessels is actually exclusion zone or structured water. Okay, and what this theoretically does is it provides a smooth and slick layer for blood cells to pass through. Okay, because blood cells, you don't want blood cells to stick or adhere to the vascular wall. And an exclusion zone water, since it excludes things, it excludes solutes, what you're going to do is you're going to produce a very strong repulsive force against the blood vessels, and this is going to help to stop them from sticking on the blood vessel wall. Now, blood flow. So again, as I've just said, there is a resulting electrostatic repulsion between the capillary wall and red blood cells, and this essentially stops them from becoming lodged or stuck. Okay, the structured water blanket provides a smooth, slick layer which the blood cells can freely pass. So what this is essentially meaning is that the easy water lining the vessels stops the blood from sticking to the sides. And so to add to that, the sulfate contained on the red blood cell membrane as cholesterol sulfate as it is coming in from the newly oxygenated blood from the artery, what it's essentially doing is it's shedding sulfate, and that means in doing so it's actually shedding negative charge. Okay, so as it's coming from the artery, it's shedding negative charge. And so if you imagine this blood cell has so much negative charge, and once it's donated that negative charge to the glycocalyx, what's happening is it's actually becoming more positively charged. As it gets towards the vein, is becoming more positively charged. Okay, so because there's more sulfate on the arterial side, as it's being deposited, you're going to have a denser negative charge on this side of the vessel. Whereas as you go through the capillary and toward the venous side, it's going to be much more positively charged. Okay, and Dr. Stephanie Seneff has essentially written in several papers about how the distribution of a more negatively charged and a more positively charged side to the vessels is actually creating a battery type system, which is used to propel or pull the blood cells through the capillaries. Okay, it's actually referred to as a voltage drop. Okay, so essentially it's more negative on the side of the artery, it's more positive on the side of the vein. And so this is essentially propelling or pulling the red blood vessels from the artery toward the vein. Okay, and so there is something which is referred to as the electrokinetic vascular streaming potential. Okay, so we've already established that the red blood cells possess charge. Okay, and if you know anything about physics, I mean, I'll be honest, I'm not very knowledgeable in physics, but this is my rudimentary understanding. When you have a flow of charged particles, it produces an electromagnetic field. Okay, and so red blood cells actually possessing charge, they travel through the blood, and the traveling of, or the flow of blood cells through the blood is actually generating an electromagnetic field. And so Seneff and her colleagues refer to this as the electrokinetic vascular streaming potential. And so this EMF, which is essentially produced from the blood cells flowing through the vessels, it's producing all of this EMF. Okay, and the EMF is actually triggering a certain enzyme which is EMF sensitive. Essentially, it's triggering an enzyme called endothelial nitric oxide synthase. It's abbreviated eNOS, and eNOS is very sensitive to the electromagnetic environment. All right, and so eNOS produces something called nitric oxide, and if you know anything about nitric oxide, it's essential for vascular health in small doses. It's actually called a vasodilator, which means that it dilates the blood vessels. Okay, and so what this is theorized to do is essentially, let's have a look at the diagram. So here is a very good diagram out of one of Seneff's papers. She's essentially saying, so this is the flow. You've got the arterial side and the venous side of the capillary, and you've got red blood cells traveling through the vessel. They are producing, because they are charged particles, they're producing an electromagnetic field. Okay, and the electromagnetic field is essentially triggering an enzyme in the vessel wall to release something called nitric oxide, and nitric oxide vasodilates the venous side. Okay, vasodilates the venous side to promote blood flow, to essentially promote vasodilation, dilation of the blood vessels, allowing the blood cells to essentially pass back into venous circulation. Okay. So if you would like a more detailed explanation of this, I did write an article on it. It's quite basic, but really the technical details are found in this paper, a novel hypothesis for atherosclerosis as a cholesterol sulfate deficiency syndrome. I highly recommend anyone who's interested in the technical details to read this paper. And really any of the other papers that Senef and her colleagues have written about this, and there's quite a few. And just to summarize then, essentially the point that I've tried to get across, and perhaps not so well, is that sulfate is absolutely essential on a biophysical level for the blood to flow. Okay, so sulfate, just to summarize, sulfate is a cosmotropic ion, meaning that it can structure water, it can produce a gel-like phase in water. Now, sulfated glycosaminoglycans form exclusion water lining the blood vessels. Okay, what this does is it stops the cells from adhering to the blood vessels, to the sides of the blood vessels themselves. To add to that, you also have red blood cells, which are dotted with cholesterol sulfate on their outer surface. The cholesterol sulfate also provides the red blood cells with a very dense negative charge. This stops the red blood cells from sticking together, but it also stops the cells from clumping up and sticking to the vessel lining. Now, when the red blood cells are traveling through the vessel from the artery, through the capillary to the vein, what they're doing is they're potentially shedding sulfate to the glycocalyx, to the inner lining of the vessel. This produces a higher or denser negative charge on the arterial side and a more positive charge on the venous side, which potentially forms a battery kind of system which helps to propel the blood through the vessels and promote healthy blood flow. Okay, so the flow of blood produces force which dilates the blood vessels through the release of endothelial nitric oxide synthase, which is actually produced by the EMF of the charged blood cells flowing through the blood. Okay, key point of everything, what I'm trying to say here is that sulfate is essential for blood flow. So how is all of this significant? Well, sulfate seems to be absolutely essential for the blood to flow. And if the blood doesn't flow, then we die. The human body drops dead. You may get a clot, you may have a stroke, you may have a heart attack, you could die. So the way that I see it is that blood flow is prioritized. Blood flow is a main priority of the body. And if the body needs sulfur, or specifically sulfate, to maintain blood flow, then I believe it's theoretically plausible that what we may actually do is prioritize that, is that we may divert our resources away from other things which also require sulfate. And really, if there's limited availability of sulfate, then I would imagine that much of the sulfate that we have is going to go on making sure that we can have healthy blood flow. So when we look at some of the other things that sulfate is needed for, well, you see, if much of our sulfate actually comes from our amino acids, methionine and cysteine, then does it mean that many of the other reactions which require methionine and cysteine, such as methylation, such as glutathione synthesis, does it mean that those things are going to be reduced? I think it's possible. So Does it mean that detoxification is going to be reduced? I think that's possible. If you look at some of the other macromolecules that sulfur is needed to produce, you have sulfur mucins and mucopolysaccharides in the gut, actually, which make up the gut lining or the gut wall. And if the body's low on sulfate and it needs sulfate, then it's going to get it from any source, and it's going to prioritize where it gets it from. So one of the first places it's going to take it from is the gut. And so could it be causing leaky gut? Well, yeah, that's possible. Could many of the other functions actually be down-regulated to be able to make up for the deficit in sulfate? Now, Dr. Stephanie Seneff has actually come up with various scenarios and made some very strong links with various cardiovascular diseases. There are lots of things that can go wrong with this system. As I said, there are nutrient deficiencies. If someone is chronically deficient in vitamin B6, in molybdenum, if someone has some kind of chemical or metal toxicity, which is, messing up with some of the enzymes involved there, you have mercury, lead, aluminium. If there's glyphosate practically disrupts sulfur metabolism in every known way. It's absolutely crazy. I swear glyphosate is sulfur's worst enemy. And again, as I said in the recent interview that I did on oxalate can actually cause the cell to waste sulfate. And so if there's a very high oxalate burden, then there's a possibility that sulfate is also going to be wasted. This means you could be getting rid of sulfate when you actually need it. And to top it all off, there are certain genetic SNPs, which might mean that someone has more difficulty accessing or metabolizing and processing and utilizing sulfur to form sulfate. And so these are things that I think need to be considered. I'm sorry that this couldn't be more practical. I'm not sure what practical significance this information could have as of yet, other than reducing overall chemical burden, reducing toxic burden, maintaining a high sulfur content in the diet. And I would always opt for the sulfur-containing amino acids, cysteine, methionine, and taurine, which we get from animal products. I would say that these are crucial. Other than that, all that I can say is that I think trying to optimize digestion, optimizing nutrient density in bioavailable forms, which is usually animal-derived foods. I think animal-based foods are much more bioavailable in terms of their nutrients. So that's all for today, folks. Thank you for watching. I hope that you found it helpful. Although it wasn't very practical, I hope that it's given you an appreciation for sulfate as a nutrient and some of the magical effects that it has on basically allowing us to live. And that there are lots of things that can go wrong with sulfation, and so these are things which I think we need to keep in mind. So if you liked this video or you found it helpful, please like and subscribe to my page. You can also find me on Facebook as EO Nutrition. Thank you for watching, and I will see you next time.